And in the meantime, I'm going to quickly review what we have seen uh, in almost 1 week ago. So we have seen there are two ways to do the row reductions. One is called the forward row reductions. Okay, row operations. We have three row operations: replacement, interchange, and scaling. And for forward row reductions, basically we follow exactly the same procedure. The procedure to reduce the matrix elements into zero is always fixed. If we fix following the same procedure, you will identify the same pivot positions. Notice that pivot positions are position where the pivots are. The number of periods may vary, like depending on the process. When you do a row operations, but if we follow exactly the same forward row reduction, then you will identify exactly the same pivot positions. The number of pivots will be always the same. There will be always 3 pivots. You will not be able to identify 4 pivots or 5 pivots in this 5 by 5 matrix. There's always 3. And you will always identify these 3 pivot position, and 1, 2, 4 will be your pivot columns. These results are always the same. You can try different operations, but then you will always identify the same pivot position and the same pivot columns if you follow the same procedure of forward row reductions. And furthermore, we can do the final stage, the last matrix we obtained using the forward row reduction is called echelon form. Echelon form looks like a stairs, 阶梯状. And then here's the definitions of an echelon form. All non-zero rows are above any rows of all zeros, and each leading entry of a row is in a column to the right of the leading entry of the row above it. All entries in a column below a leading entries are zeros. And the examples are like this one. You see the squares, the leading entries, the black little box is the leading entry. And then it satisfies all the requirements of echelon form. And it's looks like a stairs. And then all the values below and to the left of the leading entries are zeros. Okay, and we can further reduce the echelon form into a reduced echelon form. And then in that case, you will see that all the leading entries becomes 1, and all the elements above and below, the leading entries becomes 0, and everything to the left of the leading entries are also 0. And in order to find the reduced echelon form, we need a backward row reductions. And following this provided procedure, we are able to reach a reduced echelon form. Again, a reduced echelon form has a definition. The requirement for reduced echelon form is that the leading entry must be 1, and now leading entry is the only non-zero entry in its column, so everything above and everything below it must be zeros. So you use the forward row reduction first, and then backward row reduction next. Eventually, you will be able to reach a reduced echelon form. And then we have started the inverse matrix. Okay, so here are some inverse matrix properties. The inverse matrix of inverse matrix is itself. And if we have two invertible matrices A and B, then we have AB, the multiplication matrix. If we do the multiplication first and then do the inverse next, it will be equivalent to B inverse times A inverse. There's a reverse of the orders. And this is similar with the matrix transpose. Recall that we have a property of doing multiplications and then the transpose of matrix. If we want to multiply the transpose matrix like one by one, then you have to reverse the order. And here's a similar result, like the order has to be reversed. And if we combine the transpose versus the inverse of a matrix, the inverse of the transpose will be equivalent to the transpose of the inverse. Okay, and so again, we remark the most important concept right here. Like if we want to do the product of an invertible matrix is also invertible. But then if we want to express the inverse of it, inverse is the product of their inverses in the reverse order. Okay, and here's a systematic way to calculate the inverse. 要计算 A inverse 对于一个除了2×2矩阵以外higher dimensional matrix, we have an algorithm to follow. And such an algorithm starts with writing down the matrix A here. And then right next to the A matrix, we put identity matrix, which is exactly the same dimension with A. Suppose A is a m by m matrix, then we're going to put n value of ones. And yeah, we put n diagonal elements to form an identity matrix. So in the left-hand side, we have A matrix. In the right-hand side, we put identity matrix so that it becomes a n by 2n matrix. We have n dimensional n rows and 2n columns, like put it like side by side. 把 A 矩阵跟 identity 矩阵一左一右把它放在一起，然后变成一个 n 乘以 2n 的矩阵。And then we try to do the row operations, like using the operations like this. We use a similar notation. This means row equivalent. We use row operations to operate this matrix, and then like try to reduce it for after several steps, and then to see if eventually we're able to move the identity matrix to the left hand side. We wish to find a like n by 2n matrix such that the left hand side is identity matrix. Initially, we start with the identity matrix on the right hand side, but then we want to terminate with the identity matrix appear in the left hand side. If we reach such a matrix, then what appears in the right hand side, this part, will becomes your A inverse matrix. And okay, so this is an example of doing this algorithm. So we are given a matrix, which is a 3x3 matrix. So 3x3 matrix, we do not have a formula like the 2x2 matrix. So we use the the algorithms. We start with write down the 2 n by 2n, n times 2n matrix, which is 3 times 6 matrix. And on the left hand side, this is exactly where the A matrix should be placed. And on the right hand side, this part is the identity matrix. Then we can do the row operations. So you may observe that, sorry, I touched the wrong button. Okay, you may observe that the first row operation it performed looks like a interchange, like the interchange the first row and the second row, and then obtain the second matrix. And then the next matrix is obtained such that this positions becomes a 0. And then the next matrix further reduced this position to 0. And then this position becomes 1, which is reached. Okay, this position becomes 1, which is reached by dividing the third row by 2 for all components of the third row. So we are very close to identity matrix on the left hand side, except that there are still 2 positions which we need to cancel out. We want them to be 0. So one more steps, and then I get 0 and 0 right there. 0 and 0. So eventually I get a identity matrix on the left hand side. So that means that the right hand side of this 3 by 6 matrix is the A inverse. Okay, so you have to be familiar with the row reductions, either the forward one and the backward ones, and all these examples serve as good exercises for you to follow, and you can do it one time by yourself and then check the answer, the solutions in the slide, and see if the procedure matches. Okay, and here's a summary which is called a invertible matrix theorems. When a matrix is invertible, invertible means that the inverse exists. So when you hear this terms, it means that the inverse of a matrix may not exist. Means that there may not have an inverse matrix that can be written. So if you think of a 2 by 2 matrix, I think you will agree with my statement, because the calculation of a 2 by 2 matrix involve not only just a matrix itself, like you change the diagonal element and multiply by -1 on the other 2 components, but then you still need to divide it by determinant of the matrix. But the determinant of the matrix may become 0. Right, and then when you put the 0 in the denominator 分母为0, then that inverse may not exist. So now you agree that a matrix may not have the inverse matrix when determinants equals 0. And similarly, for all square n by n matrix, we may not have a inverse matrix. The situation where the inverse exists, we say that the matrix is invertible matrix. And this theorem says that all the statements are either all true or all false. So what does it mean by all true or all false? It means that if A is true, then B is true, C is true, D is true, and all the remaining things are all true. But if A is false, then B is false, C is false, D is false, E is false, blah, blah, blah. All of them are false. So you can also say that it can be stated as A implies B, B implies C, or any order, like C implies F, and then F implies I implies A. Like the implications among these items hold. So you can arbitrarily pick two and then say they are equivalent. Well, actually, you can also write the two-side relationship between any of the statements. That's how you understand this theorem. So, okay, the first one, we say A is row equivalent to identity matrix. Row equivalent. Do you still remember what a row equivalent means? Row equivalent means that you are able to reach some matrix by the three fundamental row operations. 只要是可以透过三种 row operations 所得到的矩阵，那我们就说这些矩阵是 row equivalent. The common symbols we use to denote that two matrices are row equivalent is this one, 波浪状. Like we constantly use this one when we do the forward or backward row reductions, and it directly means that, okay, this matrix is row equivalent to the next matrix. And it also implies that there will be exactly n pivot position. So what n is a dimension of this matrix, a square matrix. It also implies that only the trivial solutions can solve AX equals to 0. Trivial solution, which is X equals to 0. And it also implies that the columns of A are linearly independent. And the linear transformation is 1-to-1. And also the equation AX equals to B has at least one solution for each B in Rn space. And the columns of A spans Rn space. We have not reached the definition of span, but it means that the entire Rn space are covered. Like it's similar idea with the one-to-one transformation. The one-to-one function means like everything in Rn, you can find a input such that its output can cover the entire Rn space. But later we will formally define what span is. Okay, then the linear transformation maps Rn onto Rn. There's a n by n matrix C such that C times A equals identity, and this C is exactly A inverse, the inverse the inverse matrix of A. Do you have any questions about the statement on this page? Okay. We still have two more items in the bottom. Okay, this is same thing to say that A inverse exists, and if A is invertible, then A transpose is also invertible. Okay, then here are some examples to utilize to apply the theorem we just see. That theorem was collected as invertible matrix theorem because it starts with A matrix is invertible, and then it comes like continuously a bunch of statements, like huge collections of statements, and you will continually see that invertible matrix theorem in the following chapters. Okay, so here we are requested to determine if this matrix is invertible. So of course, we can use the algorithm that we have learned, which is we put a n by 2n matrix, putting A on the left-hand side and putting I on the right-hand side. And then to do the row reduction to form row equivalent matrices with several steps until we reach a place the identity matrix is on the left-hand side, and then here the A inverse is the right-hand side. If we are able to reach this place, then A inverse, whenever we find a inverse matrix, we can say that, okay, A is invertible. Here it is. But according to the theorem, we can determine if A inverse exists in more efficient way. For example, we can try to reduce it into an echelon form. This is an echelon form, and with the pivot position right here, I use a square to represent the pivot positions. And there are 3 pivot positions. Since this is a 3x3 matrix, so having 3 pivots positions means that okay, the one of the items holds true. Okay, C, this one, C is true. A has 3 pivot positions, and therefore all of the others should be true. So A is invertible. So we can say that, okay, now according to the theorem, A matrix is invertible. So here's the what can be seen using the linear transformation eyesight， 用linear transformation 的视角来看，那 A inverse 它做了一件什么事情呢？ So basically the linear transformation A inverse the A inverse matrix do in linear transformation is undo whatever transformation performed on the original figures, and whenever you multiply by A inverse, then we undo what has been done by multiplying A inverse. 之前我们在做线性转换的时候multiplication by A matrix, and that directions multiplication by A inverse when it's a linear transformation interpretation, we say it's either reflection, projections, and shear, and other linear transformation. If we multiply by A to the left, 在左手边乘上你的A 矩阵。But if you further multiply A inverse again to the left, 在左手边乘上 A inverse, that means you undo reflection, undo projection, and undo what has been performed on that original figures. Okay. And so the statement is said that a linear transformation is said to be invertible if there exists a function such that you can do the linear transformation of linear transformation again, and then that will undo what has been done in t function. Undo. Since this is an undo, so we get exactly the same vector x. And similarly for S linear transformation is invertible means that there exists to undo S function, we take the function t of S, and then that will undo what has been performed on S. So if such an S exists, like T and S is like a pair, T and S 是成对出现的, so that you can take function S upon T function, and then take T function upon S, and then all of them can undo, both of them can undo the other, and then retrieve X vector. So this is a pair. This is a pair. 它们是一对的。 And if such an S exists, it should be unique. 那既然是一对的，那当然是就只要它存在的话，它就只有那一个。And it must be also a linear transformation. And then we call that S is the inverse of T, and then write it as T inverse. Okay. Then this concept is analogies to the matrix inverse. Okay, the next example asks, what can you say about a one-to-one linear transformation from Rn to Rn? And actually, last time when I did the survey, I think that many of you think that the one-to-one linear transformation, basically one-to-one function, is not a very clear concept. So here's we can map with what you learn in the high school. I believe that at least it's mentioned during your math course in high school. So one-to-one function is also called injective. So injective, at most 1x could make f of x equals y. It's called injective. And also we can compare it with surjective. And it says that maps an element x to every element y in that in the range. Okay, so we have a function f, capital X to capital Y, and for every range, capital Y, all the elements, little y, a lowercase y, there exists some x in the capital X such that f of x equals y. This is called surjective or onto. These two terms are exactly the same, surjective and onto. And this is injective and one-to-one. We also have a very special or very restrictive function. This one is called bijective. And you might be familiar with the Chinese translation of that. But in English, it's called one-to-one correspondence. Like 除了 one-to-one 之外，它后面还有一个形容它的名词叫做 correspondence. So the full name of this function is called one-to-one correspondence. So you see that the restrictions, this is quite restrictive. It says that there exists unique x such that it has to say that for every y there exists unique x such that f of x equals to y, and for every x there exists unique y such that f of x equals to y. You have to say it for two sides, like unique x and unique y. This is called bijective. Okay, so even though the terms looks different, but the concept has been there in your high school book. All right, so if you still remember that to determine a one-to-one linear transformation, it requires us to check the columns of the standard matrix A, if they are linearly independent or not. And since this is one of the statements in the invertible matrix theorem, then we can also say A is invertible by invertible matrix theorem. And then also T maps Rn onto Rn. And also this linear transformation is invertible. Actually, you can say many things, everything. You can also say Ax equals to 0 has only the trivial solution. And you can also say that there exists a unique solution for Ax equals B. like everything in the invertible matrix theorems are possible answers to this specific questions. Okay, and so this is now we enter the Gaussian elimination. So here's what we have, what we call a linear system. We are collecting linear equations like this, and there's a corresponding graph for this x and y two-dimensional linear equations. You know that you draw two lines and then find out that there are intersections of them. The intersections becomes the solution of this collection of linear equations or solution of linear systems. And okay, a linear system has three status. One status is that there is no solutions, or there is exactly one solution, or there are infinitely many solutions. And in some of the questions, you may see the term inconsistent system and consistent system. So a system of linear equation is said to be consistent if it has either one solution or infinitely many solutions. Basically, there exists a solution. Or it's a inconsistent system if it has no solution. It's just a name of that, terminology of that. You just need to memorize it. So when you see the questions, you won't be shocked, like what does it mean by consistent and what does it mean by inconsistent. But basically, consistent system simply means that there is a solution, including one solution or many solutions. But inconsistent, there is no solution. And no solutions usually appear like this. You have two parallel lines and there's no intersections. For infinitely many solutions, you will see lines are all the points on this lines are intersections. And so this is a general expression we have seen before. This is not the first time to see this, but now we are formally defining it. It's called linear system, and it's written as AX equals B. And then here A should be a n by n matrix, or we simply write it as A belongs in real space n times n to the top right. And R stands for real.那这个的意思就是说，在 A 矩阵里面的所有的元素都是实数，然后它的 size 是 n 乘以 n 啊 n， 然后 m 是rows 的数量，然后 n 是 columns 的数量。This and this kind of size of A we say is n by n. And to be more rigorous, we can also write x equals vector Rn. So the size of x is n, and then the size of B is m. Okay. And so how does Gaussian elimination do? Basically, we just continuously use the forward row reduction. So suppose we have collections of linear equations, 联立方程式, put it together. And then we can write it as a matrix form by collecting the coefficients into a matrix. Such a matrix called a coefficient matrix. And I think it should be 10 right here. And so we form an augmented matrix by putting A matrix on the left-hand side and then B vector on the right-hand side. So now it becomes a 3 by 4 matrix. This one is called an augmented matrix. So review, we have three elementary row operations: replacement, interchange, and scaling. For replacement, we are replacing one row by the sum of itself and the multiple of another row. For interchange, we exchange two rows. Scaling is multiply all entries in a row by some non-zero constant. And then we will work on the augmented matrix rather than the coefficient matrix. So you see that in this 3x4 matrix, all the last columns represent the right-hand side of the linear equations. And our goal is to eventually reach such an echelon form where the bottom left are all zeros. And okay, so we do the row operations. Here we replace the second row to make here 0 and make here 0. And in this process, we identify the first pivot being 2, right? And then next we use negative a to be the pivot. And then this one is reduced to 1. Eventually we identify 1, 2, 3 pivot positions. And then we can map it back with the 3 pivot positions and the 3 pivots to negative 6 and 2, like this. Okay. And here's how we define row equivalent matrices. If formally we say that if a matrix B can be obtained by executing elementary row operations on a matrix A, then A and B matrix are said to be row equivalent. And row operations are reversible. Like through a series of row operations on B, we can also attain A matrix. Like even from starting from if A is row equivalent to identity matrix, like starting from identity matrix, identity matrix is a very special one that has most of the components being 0 and only the diagonal elements are 1s. But we are still able to use the row operations like scaling and then replacement to retain A matrix. So A matrix and I matrix can be row equivalent. And then this is something appear in the invertible matrix theorem, says that if they are row equivalent, then that means A inverse exists. And then the next remark says that two linear systems will have the same solution set if the augmented matrix of them are row equivalent. And this is why we can use Gaussian elimination. Like we reduce the A matrix into echelon form. And echelon form is row equivalent to A. And solving the linear equations of echelon form that has many of the coefficients has become 0. And then that solution X will be the same solution with the original AX equals to B. Okay, this might be too theoretical, but how many of you can understand like what we are trying to say about the same solution set? All right, so it's okay if you don't really follow what it means, but then but Gaussian elimination is the typical way that we can use to solve the linear system. This is the things you should memorize. And then if you're curious, like why, because we are actually reducing the matrix coefficients into 0, but then find the solution of the last echelon form matrix. And then if you have a question like why we can do that, then this is the answer for that question. Okay, then eventually we got the final matrix or the last matrix of Gaussian elimination, 高斯消去法, and it should be an echelon form. if it's not an echelon form, what should we do? We should continue to do the forward row reductions until it reaches a echelon form. So the solution of it is much easier to find. So we will solve x3 first. Why? Because x3 is equal to 2. We can see it directly. Then we solve x2 because in the second row we have negative 8x2 minus 2x3 equals to negative 12. So that's much easier to solve x2 when x3 is already known. And then finally x1, we have 2x1 plus 1x2 plus 1x3 equals 5. So since x2 and x3 are both known, then x1 is solved. And there's a sequence. This sequence is fixed. 就这个顺序是固定的。Please don't try to change the order or to violate the forward row reduction, or sometimes do forward, sometimes do backward, unless you need a reduced echelon form. But please just continue to do the forward reduction, forward row reduction. And this sequence is called back substitution. Substitution, 变数替换. Substitution means that we are substituting x3 with 2, and then substituting x2 with some solution, and then substituting x1, and the order with 3, 2, 1. So it's called back substitution. And the term back substitution also appear constantly in the materials talking about Gaussian elimination, right? Because it says even though the reduction is forward, but the procedure, the priority, not priority, the order you obtain the values for those unknown is reversed. We start with x3 and then find x2 and then x1. And if we do it in the opposite way, it says that if we do not reduce the matrix, the augmented matrix into echelon form, but then make the top right corner to be zeros, then in this situation we will solve x1 first, and then x2, and then x3. So this sequence is called a forward substitution. This is written here, provided to you, says that okay, this is possible way, but just not recommended, because when we define the echelon form, we want the bottom left, bottom left 左下角 to be zeros. But everything can be do it reversely, but then it will not be easier, like following the forward row reduction and the backward substitution is a typical way in the Gaussian elimination. And here's the review again, like what is an echelon form and what is a reduced echelon form. All right. So pivot position is also a review. Formally, it's said to be a location in the original A matrix. And that position corresponds to a 1 value, the leading entry in the reduced echelon form. So it's really clear if you already obtain a reduced echelon form from A matrix, the reduced echelon form of A, then you can identify those leading entries, 1, and those positions are exactly what we say, a pivot position. And then we should go back to the original A matrix to find out what the values are originally there in the matrix A, and those values can be called pivot. Okay, and the pivot column will be the column of that position, contains a pivot position. And here are like two fundamental questions about a linear system. Well, actually not just a linear system, but in a general math system, like in math systems, people the first question asked is always existence, whether some solution exists or not. And after we find out that the solution exists, then the next question is that is it the only solution? Is the solution unique? This question is called uniqueness. So what kind of well, this is the linear system, and then you are already familiar with that. But other complicated math system, like for example the GAN, the Nash game, Nash equilibrium, and people would ask if the Nash equilibrium exists, and then after asking whether that equilibrium exists, people will ask if the Nash equilibrium is a unique one. So similar patterns are applied in all the math systems. So the first things when we discuss about this, the very first question we should ask is whether it exists. So, okay, we want to determine if the following system is consistent or not. So in order to answer this question, we can just go ahead and solve for it. So eventually we identify such a echelon form, and then find out that we can use the back substitution to solve x3 and then x2, and then x1. So we can say that this is a consistent systems, and the solution is also unique just by using the Gaussian elimination to solve it. And again, we may encounter a problems like this, and then we apply the Gaussian elimination to the augmented matrix, and following a few steps, we reach a situation right here. But then we found out that, okay, here's all zero rows. This augmented matrix now in triangular form. So it means that it's already in the echelon form. So this is the final matrix of the Gaussian elimination. However, if we write down the equation notations, we find out that, okay, the first rows looks okay, looks fine. I have 2x1 minus 3x2 plus through x3 equals 1. And then the second line also looks fine, x2 minus 4 x3 equals 8. But the last rows looks awkward, because on the left-hand side I write 0, and the right-hand side I write 5/2. So that's a short form. It says that 0 equals 5/2 is a short form of 0x1 plus 0x2 plus 0x3 equals 5/2, which is impossible. So, or it's a built-in contradictions. It's a contradiction originally in the system. So this system is an inconsistent system. It's a no solution collection of linear equations. And now we define what is a linear combination. We attempt to write A matrix times X vector by linear combination of columns of A. So I can write it as okay, this is AX, A matrix times X vector. And it's equivalent to like separate the A matrix into n column matrix multiplied by x1, x2 to xn. And then I follow the rule of matrix multiplications. I can write it as x1 times a1 which is a column, plus x2 times a2 as a column, and then xn times an as a column. And this right up, this expression is called linear combination of columns of A. Or I say it's linear combination of the collection of A1, A2, and AN vectors. So this, to write the things in this way is called linear combination. And why is called linear combination? We are combining the columns by scalars x1, x2, and xn. So initially I have like the vertical a1, a2, and an, and then I want to like combine them. And then the way to combine it is to multiply by some scalar in front of it, and then sum them up. This is called combination. And this is linear combination because x1 has no restrictions. No restrictions on x1. x1 can be any values. And then also I'm just adding them up. I did not multiply them together, right? It's possible that I do combination, but then choose to, for example, x1 times a1 times x2 times a2 times xn times an. But I did not do that. So I choose to use a plus to combine them. So whenever I did this, it's called linear combination. So, okay, this example shows us how to express the matrix, the linear system as a linear combination. So this is matrix A, and then this is some other vector. So I can write it as the linear combination of the columns of this matrix A. Matrix A. I have 1, 2, 3. The first column is written right here, 1, 0, and the second column written right here. Third column written right here, and then multiplied by scalars 3, 4, 7 correspond to 4, 3, 7. 4, 3, 7. And then I do the calculations, eventually obtain 3, 6. And similarly for the second example, I want to rewrite it as the linear combination. So this part, this is called linear combination of columns of A, or linear combination of two vector, collection of two vector. To express the collection, I use braces, 大括号, okay, collection of these two vector. Okay, so that's how I rewrite. This is a original is a A times X in matrix form. In matrix multiplication form. And then I can rewrite it into a linear combination of the columns of A. And this expression is quite useful, even though you see that the computation is not, computationally, it's not affecting anything. Like basically you're doing exactly the same numerical computation. So you don't see why why it's convenient to write such combinations. But later in our lab session, the next lab session, which is close to the end of this month, you will see there are a lot of applications of linear combinations are expressed using matrix. So for example, we have the colors being RGB, like red, green, and blue, and then we are combining the portions of R and G and B by controlling the vectors. By controlling the scalars in front of it. So if we assign a large value in front of R, and then like 0 value in front of G, and then a very light value in front of blue, and then we will get probably a purple, something like that. And then the vectors values will be fixed, and then the linear combinations of RGB 3 vectors will, and then by adjusting the weights in front of it, you will obtain different colors. That's one of the very easy example of linear combinations, but there are still a lot. And it depends on how you interpret the combinations of these scalars and vectors. And even in the area of operations research, when we do the optimization, and the algorithms we attempt to find the optimal solutions require some fundamental linear combinations of two solutions. And then if we find out that there's no improvement by adjusting the scalars of it, and then we might identify there are two optimal solutions, something like that. But that's more abstract, so you can forget about it for now because you have not taken the operations research course. But the RGB case, that shows something we can see in the lab section. Okay, the next example, suppose we have V1, V2, and V3 in the Rm space. Please write the linear combination with the scalar 3, -5, and 7 as a matrix times a vector. So basically, here V1, V2, and V3 is vector in Rn. So it should be, looks like this, 3 V1, and then combining with -5 V2 plus 7 times V3. And then this is do the things reversely, like we are given linear combinations, and we are able to write it as a matrix representation. So to write it as a matrix representation, we are collecting V1, V2, and V3 into the matrix, and then multiply by the scalars 3, -5, and 7. And that's how we do this. Next, finally, we are able to define what a span is. So if I have V1 to Vp being in the Rn space, and then the set of all linear combinations of V1, Vp. Here it says linear combinations. It's the result of linear combinations. And it says all means that we can identify some scalars to combine them. So back to the examples of RGB case, we are combining the vector R with vector G and vector B. And then by choosing any number scalars to combine them together. So what would be the result of all linear combinations? Can you imagine? 就是如果我要把 RGB 红色、绿色跟蓝色三原色，然后用线性组合的方式把它们全部收集起来，那会是得到什么样子的一个集合呢？那 okay, the result of all linear combinations of red, green, and blue will be all the colors, including black and white, right? Because one combination is a specific combination of red, green, and blue, but all of them will be the colorful, all the collection of colors. And then it's all continuous because you can choose not just the integer values but you can also choose fractional values, those with yeah, you can choose all rational numbers basically, because it says R. You can choose any real numbers to be used to combine the vectors R and G and B. So the set of all linear combinations in terms of colors, it will be the set of all colors. And then here is a more general concept called span. Span of V1 to VP is the set of all linear combinations. So span is a set. span 本身是一个集合。那给定 V1 到 VP 这些向量，那它们所有的线性组合的结果收集起来之后，因为每一个线性组合的结果都是一个向量，把这些向量全部收集起来，还会变成一个 span。And then, okay, and it's also called the subset of Rn, spanned by or generated by V1 to VP. So this is quite a lengthy descriptions about a span. Like this is kind of a notation you use. You said span of V1 to VP, use a braces notation, 用大括号来表示. Or you say that in English, says that the subset of Rn spanned by V1 to VP. And here it says that this span is the collection. Collection is the same thing with saying all. Collection is all. All of the vectors that can be written in the form C1 times V1 plus C2 times V2. Always remember that V1, V2, and VP are vectors, and then we are combining these vectors using scalars. So as long as some vectors can be written in this format, okay, the result, I'll call it B for now. And then the collecting all possible, as long as it's possible, you can do the linear combination and then create some vector B's, collecting all possible B's. It becomes the span of V1, V2 to VP. Or I just use like English sentence says that it's a subspace spanned by V1, V2 to VP. And what does it look like? Geometric interpretation for span. Here span V means that there's only one vector, and span of U and V, there are two vectors. So span, like inside span, it can put, like we in the previous definition, we say there are V1 to VP. So you can put any numbers inside this braces. 在大括号里面可以有一个向量、两个向量，或是多个向量。那我们现在是逐一讨论，先从最简单里面只有一个向量开始，然后接下来就是两个向量的时候，我们看一下它的 span 在几何空间中会是什么样子的形状。Okay, suppose V is a non-zero vector in R3 space. So we work on a Hall space. 母空间 is a three-dimensional space. And then since there's only one vector, only one vectors inside the braces, 大括号里面只有一个向量. So it will be the set of all scalars multiples of V. So that will be like a set of points on the line passing through V and 0. 连接顶点 V 跟顶点0，因为零是必然是成立，因为你可以选择0乘以 V 然后得到0嘛，所以0是其中一个向量。那所有的 scalar 都可以的话，就是把这两个连接起来，然后并且延伸它，然后两边都可以跑到无穷远。所以这个是当里面只有一个向量的时候 span 长这样。那如果 if there are two vectors U and V being discussed, also in R3 space, but now V is not a multiple of U, meaning they are linearly independent. So U and V are not parallel. They are independent, then span will be the plane passing through u, v, and 0. So I have 1, 2, 3 points. One point is 0. The other is u. And then the third is v. U and v. So basically, it will be the plane passing through these 3 points. Okay, the plane in R3 space that contains u, v, and 0, because everything inside this on this plane can be spanned by u and v, and then you can select scalars. You can select scalars to form that linear combinations, and it should also contains the other side, like it's all the negative part should also be contained here, like this. The entire plane is the span of these two vector in an R3 space. So we can also say that R3 is not spanned by u and v. Why is that? Because we only spanned a subset, which is a two-dimensional plane within R3 space, right? We did not span the entire R3. Then how do we span the entire R3? To span the entire R3, we need one more vector. UVW, okay. We need one more vector that is something with u and v. So there's a property that the third vector needs to hold, the w vector. I require the third vector. I require 3 vectors to span R3 space, and also these 3 vectors must be linearly independent. So this is the important concept to describe how large the space is as a result of span. But if we only have 2 vectors, then the best we can do is to span a 2-dimensional plane, even though they are linearly independent. But it's within a R3 space with only 2 vectors, we can the best we can do is just a 2-dimensional plane. In order to span the entire R3, we need the third vector, and that third vector W needs to be linearly independent with u and v. So okay, now the following statements are logically equivalent. Equivalent means that they are all true or all false. It's similar with the invertible matrix things. Okay, the A states that the equation AX equals to B has a solution. It's equivalent to say that each vector B is a linear combination of the columns of A. Even though this one is kind of abstract, but it's also quite useful. And then the columns of A will span the entire Rm space. And then A has a pivot position in every row. Well, I agree that these 4 statements in this page is quite hard. But then initially you may just like kind of memorize it. For example, I know that if I was asked by someone like, how do you determine if the linear system AX equals to B has a solution? And I would not answer like by Gaussian elimination and see if there is a solution. I would say I can check if the right-hand side vector B is can be written as a linear combination of the columns of A. Like both solutions is answer. And I can also answer that if I can outcheck the columns of A and see if the columns of A can span the entire Rn space. Here it says span Rn, it means spans entire Rn space. Not just a subset of Rn, but the entire Rn space. And for the D statements, A has a pivot position in every row. That's by Gaussian elimination. By Gaussian elimination, I'm able to tell where the pivot positions are, and then count if every row contains a pivot position. If that is the situation, and then I know that the equations, the linear system Ax and B has a solution. Right. And here's something we have seen before, but then we can like formally review what was stated. So we'll consider a linear system Ax equals to B. And then the solution set will be the same with the vector equation. Here the vector equation is similar to linear combination. Linear combination of A1, A2 to AN, right? We have shown that 4 and 5, these two are equivalent expression. Like we can express it in either in matrix form or in linear combination form. And then also it has the same solution set. With the augmented matrix, the system of linear equations whose augmented matrix is written in this way. All of the things in this page has been shown before, but then we summarize right here. Next we have the equation Ax equal to B has a solution even only if B is a linear combination of the columns of A. So this is a quite useful answer when we were asked to determine if a system has a solution or not. And then we can argue that we are going to check if B is a linear combination of columns of A. And so a vector equation, this vector equations is again the linear combination expression. Just need to remember that A1 to AN are vectors, and also B is a vector. And it will be has the same solution set whose augmented matrix is A1, A2 to AN, and then B, like this. So we can solve it using Gaussian elimination, and then until we find the echelon form, and then solve for the solutions of that. And in particular, such a B must be able to generated by a linear combination. If and only if there exists a solution to the linear system corresponding to this matrix. Okay, so we have seen the statements like back and forth saying that like how do we determine if Ax and B has a solution? Basically, we want to check if B vector can be expressed as a linear combination of columns of A. So, okay, we may be asked to find out the possible values of B1, B2, and B3 such that AX equals to B has a solution. And here you see the term consistent. That's why we need to define what a consistent and inconsistent system are, as sometimes people are using these words, these terminology to describe the situation where AX equals to B has a solution. So consistent means that it has either unique solution or finitely many solutions, but there is a solution. And what are the possible B1, B2, and B3? Okay, it looks quite hard. Like how do we, because B1, B2, and B3 is like there are random numbers, not there are numbers, and then it seems that the numbers are not unique. So that's why the example asks for possibility. Like there are many possible values of B1, B2, and B3. If we only find one value, obviously that's not enough, right? Because there is a all in front of the possible B1, B2, and B3. Like we cannot just say, okay, like putting some values to make up the values of B1, B2, and B3, and then find out, okay, there is a solution, then the answer is just not yet fulfill what was being asked here. We actually need to find all of the possible B1, B2, and B3. Okay, so how do we resolve this issue? So here is the one way to do that. Of course, there are many possible ways. Here is one way. Like we still create the augmented matrix by putting just the abstract notation B1, B2, and B3 over there. And then again, we try to do the forward row reduction. First, letting the first two rows, first elements being zeros, and then continue to let the second element of the third row become 0. And then this is now an echelon form. So we know that in any cases of B, this will be the final matrix. And then we will start to argue about what would be the situation that there will be consistent system. There exists a solution. Okay, so it says that the third entry in column 4, which is this part, the third entry in column 4 equals to this one. And we find out that the only situation when there's a solution is that this equals 0, right? Because the only possibility is that I have B1 minus 1/2 B2 plus B3 equals to 0 is the are possible B1, B2, and B3. So there's indeed some restrictions about the right-hand side, B1, B2, and B3. And there exist other some vectors B that makes the third entry in column 4 non-zero. And in that situation, there will be no solution. So the answer is that the system is not always the system does not always have a solution. The system is not always consistent. And the requirement for the system to be having a solution is that the third entry in the fourth columns must be 0. And here is a linear combination graph, linear combinations of one vectors v1 being negative. V1 is right here, it's negative 1. And then v2 is 2, 2, 1. And estimate the linear combination of v1 and v2 that generate the vectors u and w. That generates the vectors u and w. So u is right here, and w is right here. So this is solving the example by picture， 就是这是一个看图说故事的一个问题，就是它的题目是用图的方式来给题目，然后呢，希望我们可以用图来估计出U 跟 W 它大概是要多少比重的 V1 跟加上多少比重的 V2， 分别可以得出W 是在这个位置嘛 ，OK， 所以我们要找到U 等于 something we don't know times V1 加上 something we don't know times V2. And then similarly, W is a question mark times V1 plus another question mark times V2. And the example asks us what are the values for the question mark and question marks. Okay, so that's how we were asked to estimate 估计. So we need to roughly find out the values of the scalars that can do the combinations of V1 and V2, but then eventually the result is U and W. Okay, and there is no solution. Okay, let's roughly estimate it. Okay, I would say it's roughly 2 for W it's roughly 2.5 V1, and then like negative 0.5 V2. So I would put negative 2.5 V1 plus negative 0.5. Negative 0.5 times V2 as the estimate of W. And for U, it's obviously exactly 3 V1. So I would put 3 V1 here. 3 V1. And then how many V2? Negative 2 V2. Negative 2 plus negative 2. Do you agree? Okay. So it means that I move V1 for 1, 2, 3, and then move V2 toward a negative direction for 2 units. 1 and 2. And then the linear combination of them will be this point. So that's how I create linear combinations for any points there. And also you can see that what would be the span of V1 and V2. Since V1 and V2 is V1 and V2 are in R2 space, V1 and V2 belongs in two-dimensional real space. So span of V1 and V2 is exactly R2, since V1 and V2 are linearly independent. So they can span the entire R2 space. And then you can see that, okay, the linear combinations of V1 and V2 is actually the entire Rn space. And linear combination, collection of all linear combination is exactly how we define span, the span of vectors. And in the previous example, the process we use called the parallelogram rule for addition. If U and V are two vectors correspond to 2 points in the plane, and then U plus 1 will be the vertex, the fourth vertex, 第四个角，平行四边形。Parallelogram means 平行四边形, and there are 4 vertices in this parallelogram. 平行四边形有4个角，那其中3个角分别是原点 U and V. 3 of the vertices are the origins U and V, and then the fourth vertices will be in U plus V. So this is called parallelogram rule for addition, like addition. In order to find out the addition, you create a parallelogram. 我们做一个平行四边形作图，那我们就会找到 U 加 V 的这个它的在空间中的位置。Okay, so the next example, now we are having a 3-dimensional vectors A1 and A2 and B. Determine whether this vector B can be generated or spanned, can be spanned as a linear combination of A1 and A2. That is to say, we will need to determine if there exists some weight x1 and x2 such that I have such a relationship, x1 times a1, and always remember that a1 is a vector. So this equation 1 should be written as this way. There's a vertical vectors a1 and a2, and then b1. Okay, so the similar expression is like this. By replacing the A1, A2, and B by the numbers provided to us, 把就是 A1, A2 跟 B 的这些数字带进去之后，然后呢，现在就是然后写进去之后，它就呈现一个 vector 的形状嘛。那最后再来决定说 x1, x2 有没有存在 x1, x2，然后可以使这个 equation 成立。如果有的话呢 if there exists such an x1 and x2, that means that the answer is yes. B can be generated as a linear combination. If you cannot find such an x, like it's there's an inner contradictions, like you are unable to find x1 and x2, then the answer will be no. And now you're familiar with this linear combination. We have an interchangeable relationship between a linear combination expression. This is a linear combination expression. And then you can write it as a matrix vector multiplication, right? By collecting A1 and A2 together. 1, -2, -5, and 2, 5, 6 times x1 and x2, and then equals to 7, 4, -3. And suppose this is A matrix, this is X vector, this is B. And then this question is equivalent to ask us if such a system, this system, has a solution or not. If we can find solution X, then the answer to this example is also yes. Okay, so in any cases, eventually we aim to solve a system like this. This is a system we want to solve. And to solve it, we can reduce the augmented matrix by putting the right-hand side B right next to the A matrix. So this is A matrix, and this is B vector. And then eventually we reach a form called echelon form. And then we try to solve for the equation. We find out that x2 equals to 2. x2 equals to 2 and x1 equals to 3 can do the job. So to answer it, we find out that B is a linear combination of A1 and A2 with the weight x1 equals to 3 and x2 equals to 2. So the answer is yes. And the next example says that we have A vector, A1 vector, A2 vector, and B vector. Then span of A1 and A2 will be a plane. Since A1 and A2, by observing that there's no multiples relationship， 就我们发现 A1 跟 A2 它们之间并不是一个成倍数的关系，所以它们是 linearly independent。那这个 span 呢，它是表示说它这两个 vector 它在三维空间中是一个二维的平面。Since A1 and A2 are linearly independent, but they are only two vectors, so we can only span a two-dimensional plane. The plane should through the origin all the time. 这是 subspace 的一个 requirement. 当我们到定义 subspace 的时候，又会再重新的 reach 到一次。不过这个结果要先有一点印象。我们这个 plane 总是会穿越原点。然后 the question asks us if is B in that plane. So we can either use the linear combination. Basically we're collecting A1 and A2 times x1 and x2 equals to B. Is B in that plane? Now we can use the result. If B is in the span, that means the system has a solution. These two are equivalent. 就是这题目虽然问我们说 right hand side B 是不是在 span 里面，那我们可以把它连接到说如果 right hand side B 在 span 里面这件事情是 true， 那么代表说线性系统 AX 等于 B 是有解的这样的一个关联性。然后我们来试图去求解 AX 等于 B， 看它有没有解。如果它有解，那B 就是在这个 plane 中。如果它无解，那 B 就不在这个 plane 中。So what we follow is again to the Gaussian elimination. We work on the augmented matrix, and eventually we find out that there is no solution in this as a result of Gaussian elimination. So we can connect it with the sentence says that B is not in the span of A1 and A2. Okay, so the last example is quite applied example, so you can take a look at your own. And so we're done for today, and then today we have a homework due. Do you have any questions? If there's no questions, and we're done now, and then thank you all. Have a good afternoon.